Okay, before we start, you should make. Can you read that?
Do you want to change the resolution?
No, it's fine. I think everybody can guess that this is HTTP. So if you want to win one of, I think, two start with Hazelcast second edition books. That is a book that a fan of Hazelcast, an outside fan, wrote. Second edition, pretty nice book, gets you started pretty quickly. So just go to the URL, put in your address, put in the code. That is pretty important and obviously pretty hard to get right. I think the raffle will be tomorrow sometime. So you have the whole night to do that. Okay, to the actual topic, everything is in the same size of the letters, which is obviously wrong. It is distributed computing with Hazelcast. So Hazelcast is obviously part of the topic. The URL is always on the bottom, obviously, but the examples are just the only bit where you can see Hazelcast. So all of the ideas, all of the stuff is pretty general and also goes into the direction of a general distributed computing idea. Okay, I was a couple of weeks ago in Brazil. I think all of you guys are good friends with Brazil. That is what the guys look like after the talk. And because I want to have the same thing here, we're going to try that. So everybody stands up, and we're going to do a bit of dancing. It never works. Why? He was so close to stand up. He was so close. It never works. But the important thing is interactive. So it's a Java user group talk, right? So we're not at a conference. We're not doing this teaching at universities. So we're making this interactive. Interactive in this case means I'm doing some live coding, and you tell me when I do wrong. So that is how easy Hazelcast is, and you figure it out. To try that, we're going to play a little game. The rule is easy. I ask a question, you say yes. Normally not the question you want to answer with yes, but in this case you want to like. So, have everybody read that? Yes, perfect. Okay, this is me, I guess, sometimes, especially in summer. This is pretty much what I look like, with a bit more here. I'm Chris. I think in Portugal, my name might work. I guess you guys are able to pronounce it. Try it in Japan, it's quite fun. So Chris is the easy way. Everybody gets that right. Everybody has a Chris in his neighborhood, even in Japan. It's pretty cool. I'm a Twitter fanatic. If you want to have a full timeline coming up every second something, follow me, otherwise don't do that. Pretty bad idea. Java plus 9 years is not 100% correct. I think by now it's 11 years. I started Java quite early, left it as fast as I joined it, because it was at that time everything that people still believe Java is. It was memory hungry, it was slow, it was just a bad thing. It was like, why does anybody ever would love to code in Java? And I went back to C++. Today I wouldn't say that was the best idea, but I had this feeling it might be a good idea at that time. I came back in Java 1.4, end of Java 1.4, going to the amazing Java 1.5, a totally different world, and staying in Java since that. I pretty quickly figured out that the most important topics for me are the ones that nobody else is interested in. Performance optimization, JVM internals, all this weird garbage collector stuff, the things that nobody wants to do. So if you have somebody in the company that loves doing garbage collector optimization, you probably can change with me here. But it's very uncommon to have that. It still says Apache committer, and literally it's true. Unfortunately, the project I was working on, Apache Direct Memory, retired. It went to the attic retirement. Does anybody know how Apache Foundation retirement works? Or why a project is retired? Yes. Well, it basically, sorry?
Yes.
Okay, how does it work?
It was supposed to be a question.
Oh, okay.
Everything is yes, you know.
Okay, gotcha. So retirement in the Apache Foundation basically means, or when a project project retires, it means there was no risk activity. So we were 6 or 7 people, and none of us had time. Unfortunately, the project eventually retired because there was just nothing we could argue against it on the committee meetings. If anybody wants to reactivate it, go ahead. It would be pretty cool to see Derek Henry stand up from the dead again and rise. A bit to my history, gaming. Unfortunately, I have the wrong t-shirt today. Normally I have a nice Hazelcast t-shirt, which on the back says, all your cash are belong to us. I'm not sure if there's gamers. They might understand the idea. So I was working for Ubisoft for quite some time, doing game server optimization, obviously optimization, performance stuff. I worked for HRS, which is the German Expedia thing, which is bigger and better. At least I believed at that time. We recreated the underlying booking system, the thing that takes all the hotel rates, tries to figure out the best offer, all those kinds of things. And hopefully, when you say order, it will book your hotel room. And not book it twice or not at all, hopefully just once. Exactly once. So yeah, you see pretty much all this fairy tale GC performance stuff. This is one of the nice URLs of my blog. Kind of fairly often updated blog. The last blog post is from February, I guess. I would love to write more. Unfortunately, I can't write about things just because I have the feeling I have to. So I have to have the feeling it's something important, something I want to tell people. Maybe something I went crazy about for a week just to get something right. For example, OpenShift. I'm so close to call it OpenShift because it just doesn't work. No offense for that. Some company told me it's still the best of the worst options. That's a way to put things. Okay, distributed computing. I think everybody has a data center at home. No? PlayStation 3, PlayStation 4, a couple of computers. I get them all. I get them all. So the interesting thing here is the PlayStation 3. Does anybody own a PlayStation 3 here? Okay. What you do with the PlayStation 3 in the beginning?
Just stream stuff.
Well, you could install Linux.
Yeah.
That was the whole thing. And yeah, right. So a lot of universities bought PlayStation 3s because it was an easy and very accessible and cheap cluster. Just buy 200, 400 PlayStation 3, install Linux, and you have a computing cluster. I mean, it has 8 cores plus 4 or something else, these DSPs. It's a pretty cool thing. And then somebody decided, hey, well, you can run Linux, it means you might be able to run burnt games. No, we don't want to do that. So if you want to have a PlayStation 3, go to your local university. I think we just passed by some university here. They might have one. So if you want one, just ask them. They probably are happy to get rid of them. But the idea is, well, yeah, a lot of people by now have more than one computer at home. In theory, you could do distributed computing on that. Obviously, it's not the best idea because all of these systems are different in capacity, different in CPU speed. But to make sure that really everybody has a cluster at home, let's go to the kitchen. Right? Does anybody disagree that that all of these systems have a full-blown computer, a full-blown CPU, a full-blown RAM? It's pretty weird, right? I mean, like Cattle has a MIPS or an Intel or whatever CPU, and in theory it would be able to run Linux if somebody would hack the bootloader. There are people doing that. In Germany, we have the power grid, a very cool invention. I'm not sure how far you are with the power grids, the intelligent power grids. These things can tell you that overnight there's less power consumption than over the day, or in the late evening. Well, you could hire a person to do that, but it's more cool to do this in software, right? Maybe as long as somebody figures out how to inject the virus into the system and there is no power at all. But intelligent power grid, a new way to go in Germany. Again, here, as I said, all of these systems have CPUs. In theory, obviously, a distributed computing cluster won't look like that, but you would be able. I mean, look at the ARM CPUs, these small systems. The first hosters in Germany started to offer ARM CPU-based servers for 10 euros per server, something like that per month. Based on, not on Raspberry, I think it's the Adreno, whatever, something like that. So yeah, very possible. It has to have, right? It's a cat. We all know that. So after that, it gets more serious, maybe. So what does distributed computing mean? Is here anybody who ever worked with distributed computing system? Okay. What would you say is distributed computing about?
Machines talking to each other to accomplish some job.
Yeah, that's a good start. I would put it that way. It is mostly about parallelization and splitting tasks into smaller chunks and trying to compute them in a huge amount of systems in parallel and in the best way possible. So parallelize the whole system. We'll figure out how that works. So, as I said, you're going for more servers instead of one bigger machine. Normally, this is the Oracle joke. I just learned we have someone for Oracle here, so that today it's the IBM joke. IBM can do the same thing. Whenever your system gets slow, you just call them. They sell you something which is twice as fast and triple as expensive. No problem at all. They can do those things. But the whole NoSQL area, this is not specific to Hazelcast or Cassandra or anything, the whole NoSQL area goes to the direction of having more systems, having cheaper machines, and all let them work together. And Moore's law already created this monster, and it won't work for a long time. I mean, try to add some more muscles, at some point it will probably explode. Okay, for Hazelcast, it's not only about in distributed computing. The more important part is for us is in-memory computing. This is specific to Hazelcast. In-memory computing means you store as much as possible in RAM to have fast access, to have fast computation, to have everything that starts with fast. So in-memory computing is obviously fast. I think we don't have we can't disagree that the caches and the CPU are still the fastest things. I would love to have a RAM with L1 cache access times. That would be awesome. If ever somebody wants to create that, I'm the first person to buy this. But main memory is 100 nanoseconds, and even if you look at the 1 gigabit network, this is still very fast. And that is an SSD. I mean, it's 15 times slower than going over network to some other machine's RAM. And that is a pretty fast. You can't read that. It's 4K, so it actually tries to read a fairly big block. And 1 gigabit is not the fastest network you can get today. There are systems with 10 gigabit. Our test lab has 40 gigabit solar flare cards. Pretty scary stuff for Turkish government or for Turkish customs. We tried to import them to Turkey, to our data center, and it's stuck in customs for a half year. They probably thought we were sending over a high technology bomb or something, I don't know. From California, obviously, US always does such weird things. I mean, we all know that. So 40 gigabit solar flare cards are really, really nice. They get round trip times between two different nodes in nanosecond range. This is absolutely amazing and absolutely expensive. But if you're a bank and you have a terabyte or 20 terabyte of data and you want to keep them in RAM, you buy 20 servers, 1 terabyte each, you probably have some money left for solar flare cards. Okay, the second reason for in-memory, this chart starts at 1980. With 625 kilobyte. This sounds like very familiar with 640. Who remembers 640 kilobyte times? Do we ever need more? No, right? I mean, he was he was almost correct. It's not that bad. It ends in 2013 with a typical target size of 16 gigabytes. I think 8 to 16 is still kind of true. I probably am at the higher border, so my computer at home has 32. As I said, I work for the gaming industry, so I'm probably not normal. But I think 8 to 16 is still pretty typical, pretty common. The second line, and that is the more important one, in 1980, 640 was kind of affordable. We all know that. We had systems having 640 kilobytes of RAM. But the second wanted to go higher, and that is the second line. It's the price per megabyte. If you wanted to go over the 640, it was about $6.5K. $6,500 per megabyte. Well, there was a reason nobody needed more than 640. And we see it's constantly going down. In 2013, we were at less than a cent, at a 0.005 cent, which is a half cent, $0.005, which is a half cent. Pretty nice. It kind of stabilized at that range, at least for the moment. It will probably go down even further, but we know that the RAM module is getting bigger and bigger. Yesterday in Ireland, somebody asked a nice question. There is a new technology, non-volatile RAM. That's what they call it. It's only 10 times slower than normal RAM, but it's non-volatile, so it won't lose data when you switch off power. That's actually a quite interesting thing, because that could be the real next thing for data memories. It could, with the blink of an eye, it could destroy the whole spinning and SSD scene. The only question, I see you're nodding your head, the only thing is, what will be the price? We're getting one of the first modules from Intel, and I'm really looking forward to that. That might be very, very interesting technology. I think there are three different technologies at the moment competing for that. I think so. Intel is one, and I think there's Toshiba and something else.
But are you planning to use that with JVM?
Well, the technology is commonly available. So you can either, as far as I know, you can just use it as a block device, or you can make it a virtual disk or whatever. So it is available. You just need to map it into RAM or whatever. We're thinking about doing something like a very fast tiered storage, where you just store it in RAM and immediately write to the second tier layer. Well, at the moment, as I said, we're waiting for the first models, and we're just looking at that. Everything is just fantasy and well, maybe nice fantasy. Could be very, very game challenging or game changing. Okay, so we figured out that if we want to store data in RAM, we still have a limit of available capacity. Today, you can buy servers with a terabyte of RAM. They're kind of affordable if you have this, as I already said, if you have this need for those amounts of data, you probably have the money. But going above a terabyte is still very hard. Amazon somehow managed, their new virtual machines have 1.5 terabyte per virtual machine. I don't know what these systems look like. That's pretty scary. Does Oregon have something like that? To be honest, I haven't looked at the cloud yet. I just saw this new Amazon thing with 1.5 terabyte per virtual machine. And I have no idea what these systems look like. I mean, you just don't run one virtual machine per system. So anyway, so when you have more data than you can store in a single machine, you have to partition the data. You have to shard it. Sharding is the old word for it. And if there is a database administrator, I don't think we have one here. Okay. So sharding is like the thing that came up with relational databases. Most of the time, because either one database was too slow, or it couldn't hold all the data in a reasonable amount of correct time. So what happens is, well, sharding mostly works with number ranges. number ranges. I think every good developer, even the C++ guys, now figured out that number ranges are not a good idea. It took some time, especially for the C++ thing. They're slow with everything, even singletons. But eventually all the things even end at their point. So the thing why sharding and number ranges are bad, it's not if you want to scale up. You can always add a new number range, add a new machine. It's not a problem. The problem is scaling down. If you either have a very good running country or you started too big and you want to scale down because you figure out, hey, Mexico just has the need for maybe 2 servers instead of 5. And going down and changing those number ranges and rearranging those number ranges can be pretty scary. And that is normally where database administrators or operation guys start dropping tiers, start writing Python or Perl script or whatever they love or hate and have to use. So sharding has a bit of this bad reputation. If you ask a database administrator for sharding, he's normally like, no, we don't do that. That's devil's work. For NoSQL systems, partitioning is a pretty simple and pretty common thing. Not all of them. There are still some systems, or there are some systems that replicate data, where every node will have the same set of data, the exact same set of data, but that means you can't grow up until all the machines grow the same way. So partitioning does the same thing as sharding, but on a very low-level base. It's one of the common features of most of the NoSQL systems. It means you kind of automatically and transparently to the user put in data, the system figures out, okay, this goes to that partition, and the user doesn't realize there's a partition. He doesn't know where the partition is. Everything is completely transparent and invisible. So, how does that look like in reality? This is a bit of a specific part for Hazelcast, but all of the systems kind of work the same way. You have a map. This is, I think, a Guava map. For Hazelcast, it would be a Hazelcast map. For Cache, it would be, I think this thing is called cache, whatever. But all of them look kind of like a key value map system. So there's a key, we have an object, and we put them in. And what happens underneath this, Hazelcast serializes the string into a byte stream. You can't see this here. We take the hash code of the byte stream. And this is not a Java hash code. This is a consistent hashing. Consistent hashing is necessary because you want to find your data. You just don't want to put them. You also want to want to be able to retrieve them afterwards. So for the same input, you always have to get the same output, which is our hash code here. And then you have a number of partitions. And you take the hash code, the modulo operator, and the partition count, and what comes up is the partition ID. Pretty easy mathematical formula. It just gives you a nice partition ID, and then you look up the partition table, which says, okay, I know the node that holds this partition at the moment, so I'm just going to send this operation directly to the system. This is even hidden from most of the internal developers of Hazelcast. There's a cluster service. He knows about the partition table. He creates those partition tables. He manages system failures, and if a new node starts up, he handles all the migration internally. So most of this stuff is completely hidden. But the very important things here, consistent hash function. As I said, you don't just want to put data, you want to be able to retrieve them. Therefore, you always have to have a consistent hashing in place. Whatever it looks like, somehow it must give you the same result for the same input data. Partition count must be constant. It's kind of true. For Hazelcast, you can't change partition count at runtime. You would have to restart the cluster. Other systems can do that, but what you end up with is you do this whole calculation for every single bit of data, and it is exactly the same thing as restarting the system, because you definitely have to rearrange everything. It just doesn't make sense to do that at runtime. Well, and with the consistent hashing and the partition ID and the knowledge about the partition table, Hazelcast has two deployment mechanisms. You can either embed Hazelcast into your application, he has to add another round trip to get it to the right data. So, demo time. It looks good that you guys don't have tables, because that can't happen for you. Okay, let's see. Get some water. Well, I'm from Germany, for these. This is definitely water. So the first thing you always need when you want to have a cluster is a cluster, somehow. So I already heard you haven't tried to use InfiniSpan. Otherwise, you probably not sit here, but still crying somewhere in a dark corner like, it just doesn't work. So normally setting up a cluster is pretty heavy and a lot of work. For Hazelcast, we all try to do, everything we try to do is about simplicity. Either getting the developers started quickly or making it easy to access. We will see a couple of those things. Or even just start up a cluster. So how do we start a cluster? Hazelcast has something which is called a Hazelcast instance. You can argue with the name. I did that when I joined the Hazelcast, but well, that's it. An Hazelcast instance is like the entry point into the whole API. Everything that Hazelcast offers is somehow connected to the Hazelcast instance. But to create it, it is just this line. So if I start that up, it will actually create a Hazelcast cluster. Obviously with exactly one node, which is a huge, monstrous cluster. Some people would say this is not even to be called a cluster. And therefore we just started a second time, doing some black magic. This is actually one of the important things when you join Hazelcast. It destroys networks. It eats your network cable, literally. It has to. Otherwise, there's no reason why the guys don't like multicast, because it's amazing. And what you can do otherwise is, there are different options. So multicast is nice to get started quickly. As I said, hey, this is what Hazelcast is mostly about. If you don't want to do those things, for me, I bound the discovery to my local interface to make sure at conferences there is nobody with a Hazelcast cluster running and I'm destroying his presentation, or he's destroying mine. But you can also give it a set of known members. You don't have to have all members. You can have 20 member nodes and you just know 2 or 3 of them. As long as those 2 or 3, at least one is running, everybody will join the cluster topology share. There's AWS discovery, there's JCloud's discovery, which pretty much handles all other clouds. And in the new version 3.6, there's a discovery SPI where you can build in everything you want, no matter if it's Zookeeper or what is the Netflix thing? Histic? No, I can't remember the name. No, they have something like Zookeeper. I can't remember the name. So whatever your system uses to find other services or service nodes, you can just build it in. It's pretty simple and pretty easy. And well, yeah, as I said, multicast, I just disabled it. Because sometimes, especially at conferences, there's a high chance the network doesn't support multicast because it eats your Wi-Fi signal, not only your network cables. It is pretty hungry. Okay, so now we know how to create a Hazelcast node. Let's remove this for a bit. Going back to the map example. We take the standard Java util map and we call it map. And how do we create a map normally? New? Good. First one. Hash map. Hopefully you're already on Java 7 at least. Otherwise it will look ugly. But yeah, that's it. Looks good so far. Works as expected. We can do some random number generating, like 1,000 very random elements. Map put I value I. This is my technology. I call this pseudo-random generator. I'm not sure if somebody ever found it before me, but I like the technology. So this works obviously in one thread. It is a problem if we have multiple threads. So what do we exchange? What do we exchange to make it multi-threaded?
Concurrent hash map.
Perfect. Concurrent hash map. Okay, works with multiple threads. Looks good so far. What do you think we do to make this distributed? You're not allowed to answer. You probably know the API. Same goes for you.
I was not going to answer anyway.
So the idea is pretty simple. Get this back. So as I said, the Hazelcast instance is like the entry point into the Hazelcast system. So what you do is you ask Hazelcast, hey, I want a map, and please refer to this map as Coimbra. It doesn't matter as long as all nodes agree on the same name. Okay, so let's run this. There's one thing, and you have to believe me that it is different from the first run, because I haven't told you. There is something which says initializing cluster partition table. I talked about the partition table and where the assignment to the partitions to members is. Currently, it's pretty easy. There's one member. Where is your data partition? Well, maybe this member. Hopefully, this member. But we can actually prove that we can access those data from a different node. So we're going to add some important business logic. Logging. Everybody knows logging. Everybody knows that logging is a very important thing of every system. And since Java util logging totally sucks, we all know that system print line is the way to go. Okay, please give me a random number between 0 and 1,000, maybe not 500. 42. We have to work on the interactive part. So we're connecting. And it says value 42. So we have a separate JVM, still the same system, but a separate JVM which connects to the other one and can retrieve the data. That would even work if I asked you for another laptop and do the same thing over Wi-Fi. That is what we do at conferences, and that is what people really is impressive. Like just 5 minutes coding on 2 laptops, and you have a distributed cluster working over Wi-Fi, sharing data. Okay, so far you believe me, hopefully, that we can actually access data from a different JVM. Now we do something different. Now we want to see how data distribution really works. Because currently we just saw, well, there's one node and the other one can connect and ask something. This is not what we want. So we add something that every good Java program needs. Is there any Java program that doesn't have at least one thread sleeve somewhere? I don't think so. By the way, for the more cooler systems these days, you use that. You can make your colleagues look pretty weird with that. They're looking 5 minutes like, why don't I know that? And you can make it even better. You can pass in the time unit type as a parameter, and somewhere else you hide something like that. That is amazing. That is like the best technology ever. Okay, so what we do is, obviously, we put in one element at a time, every second, a new one. So we leave this running down here. And we're going to do something else. So now, in a normal Java application where there's one JVM, you can put in data into a typical map, and then you set a flag or something. And some other thread will put it up, will look at this flag and see, oh, something happened. Okay, works so far? Now you have 2 separate JVMs. How do you make sure to realize that something happened with the system? What do Java programmers normally use to be notified about something? Yeah, what is the thing called? Right, a listener. Exactly. So that is what Hazelcast, for example, offers. So we have the important my listener, and we have implements, and we want to see that something is added because that is what we currently do. So we say we want to have an entry add listener, obviously fully generic, compliant, string, cap, an integer and string. And again, the important business logic you already know, some logging. Okay, so now we have a short problem. We have a map. So how do we register a listener on a map? I think there is nothing in the map contract. The way to go is actually using the Hazelcast extension of the map contract, which is an IMAP. The I doesn't mean interface. We're not in C++. We don't need to make those things obvious for users. It is just like every Hazelcast data structure that is extended has an I in front of it. It is called intelligent map, important map, instance map. It has so many synonyms. It is just an IMAP. We couldn't decide on a single thing. And if we look at the IMAP, we see that it is not just, where is it? And there you go. It is not just a map. It actually is a concurrent map. So it has all the nice atomic operations like replace, put if absent, and all of them are implemented obviously in an atomic way. So the thing for the IMAP is it adds functionality which is cool to have in a cluster environment. For example, where are you? Nope. Where is it? There you go. So we all know that put takes a key and a value. How many people are aware of the fact that a put returns a value? What does it return?
The old value.
If there was an old value previously assigned, exactly. So now imagine you're updating a value which is 200 megabyte in size, and you put it into the cluster, and it returns the old value, sends it over the wire, just for you to make sure it is thrown away and collected by the garbage collector, because a garbage collector wants to do something. It is pretty bored otherwise. So obviously not a good idea. So how many people ever used a return value of put?
Yeah. Excuse me. Yes.
For what? Give me just one reason.
I don't remember now, but I'm sure that I already have done that.
You're not talking about a concurrent map put if absent, which is a different thing. I would agree with that.
Yeah. I'm not talking about that.
Okay, you're not talking. Okay. You shocked me. To be honest, I think I used it once, and I wasn't aware of the fact what it actually does.
I already used it. Not many
Okay.
times, of course.
Yeah, so maybe there is one use case just to know that there was something before, but normally it doesn't give you any guarantees because it's not atomic. So if you use this put return value, it doesn't give you any kind of guarantee. It doesn't give you even the slightest idea in a multi-threaded system. Therefore, it's pretty much useless. Maybe there is a use case I never found. As I said, I'm not talking about put if absent. If you have something with put if absent and it returns a value, it means exactly at that point where you try to put in something, there was something assigned. And it returns this assigned value and it doesn't override it. So it's a very different thing. The problem with the normal put operation is if you return this value, as I said, and you throw it away, it just generates network traffic, unnecessary network traffic. And Hazelcast has some versions of those methods that work differently. Obviously, thanks to Java, you can't use the same name for a method and change the return type. So we had to call it set. Same thing for remove. Remove returns the old value. The use cases are pretty limited. So Hazelcast has a delete, which returns, I think, Boolean at least. It was somewhere. Whatever. Okay. But it also adds nice things like listeners. we figured out that much. Okay, so, whoops, wrong one. I'm making more jokes. So we have a listener. And that means we want to add this listener. And the second parameter is exactly the same thing I was talking about before. So the second parameter tells the listener to include the value when you fire an event or not to include it. In a lot of cases, you're just interested into the key and you don't need this value at all. So in this case, you put in false. For this example, we definitely want to see the values. So here's our still running member, and we're starting the same. We change code, for example, twice. Maybe we'll start the second time. There you go. And they connect to the cluster. And we see events dropping in, and we see that the third connect just came in between. So far, so good. So something works. The first node is pushing data, and the second and third node definitely going to get the events. So far, so good. Imagine you have an order system. That is probably not what to do, and not what you want to do. You have an order system, and you want to put in orders. And for every order, you want to send out the confirmation. 95. That node got 469, 96, 97, 98. As I said, the first node also gets some of those. But you will never find the same number twice, because there's only one owner per data set, or per push data. So now this is exactly what we want. If we have the order confirmation mail, we just get one send and only one. Perfect, exactly what we want, and we see that data distribution actually works. Okay, questions so far?
If a node goes down, what will happen to the partition cycle?
If a node goes down, so by default, Hazelcast keeps a backup of every data structure. That is the default behavior, always one backup. That means if you have two nodes, you have a full replication in theory. If you have 3 nodes, the backup distribution gets further. So when a node goes down, what happens is the other members of the cluster realize, okay, this node doesn't react anymore. Instead, they mark against that, they remove it from the cluster. And the guys that are owning the backup will reactivate the backup and make sure that the data is available as fast as possible. And eventually what will happen, some migrations going on because the partition number doesn't change, so the backups need to be activated and eventually migrated to have an equal distribution. If that makes sense.
For example, when you restarted this node number 2, right? Where was the data going which was meant for that number 2?
I probably killed them too fast. So I had 3 nodes running. Normally what you have to do is you kill one node, and then you have to wait before the other 2 nodes get back in a healthy state. So before the cluster gets in a healthy state, because that means backups are activated and partitions are migrated and backups are recreated.
So the node number 1 was waiting for the something to be revealed, supposedly.
If you have 3 nodes, 2 nodes are waiting for the cluster healthy state. If you have just a single node left and he has all the backups, obviously this is an easy thing. You reactivate the backups and he will be the owner for all partitions anyways. The interesting thing is if you have more than 1 node left, because then you have to activate the backup, you have to make sure that partitions are migrated and cluster gets back in a healthy state. And a healthy state also means that all the backups need to be recreated. Because now you might have some partitions where there is no backup anymore.
Is it possible to have the backup entity in a different machine of the
Yes,
cluster?
you can do that. You can create backup groups. And backup groups are things, or are designed for things like you have multiple racks and you want to make sure that one rack holds exactly the backup of the other one. But it gets even further down, so you can do pretty funky things with that. But the rack thing is the most common one.
Because the coils do the same automatically. The backup entity is saved in the different machine, if it's possible. Right?
Yeah, so we have this automatic based on IP addresses, but that means you have to create some rules for IP addresses. And if, for example, multiple nodes share the same IP address and just different ports, that works. If it is a virtual machine on the same server, and they have different IP addresses, that might be hard to figure out.
You can configure
Yeah, right. You can configure rules for that. But this is hard to do automatically. Because with DHCP, you probably doesn't even have the slightest idea of how the IP addresses are arranged. Kubernetes is pretty nice on that. If you, for example, have one namespace per machine, then there's definitely a one IP range per machine, which is quite nice. Okay, any more questions? Okay, let's go back to the presentation. Still, nobody looks like that. Pretty good. Take this thing again. And I would say that was easy. Does anybody disagree? That wasn't too hard, right? The important thing is here, anybody an independent consultant? If you're ever going to be an independent consultant, don't tell anybody how easy it is. Maybe 2 weeks, earn a lot of cash, and don't tell anybody it's that easy. It's bad for your job. Okay, second part. I'm moving to that side again. Not going to my computer. Parallelize processing. We talked about that. This is one of the main ideas of distributed computing. So I think this picture is pretty good. In the beginning, I had a picture of Chinese workers in a fabric. Then there was the Foxconn thing, and I have the feeling we can't do this joke anymore. So this is a scientist lab. Same idea. All these guys probably work on the same thing in parallel. And well, maybe they even figure out the same thing at the same time. It might be pretty funny if all of them jump up at the same second, like, I did it! Shit, all of us. Okay, parallel processing. So how does that work? Functional programmers. Do we have some functional programmers here? No function. 2, perfect. It's always you guys. So what is important about functional programming? Maybe you can already answer that. There's one important thing which is true for all functional programming languages.
Well, you pretty much implement that.
This is the important thing. You never ever want to have shared state. You never want to change shared state because it means you have memory barriers, you have to guarantee visibility. The same language, both was basic, but it was a totally different thing. And it is the same thing with Scala. It's the same language, but the functional way is just easier. It feels better. It feels just right to do these things in a functional way. Same for Java 8, using the Scream API, using lambdas. It kind of just feels right to do those things. It looks weird in the first place. A lot of people were like, "What is this arrow thing about?" But by now, most of the Java developers figured out how lambdas work. And it just looks better than an anonymous class, doesn't it? A bit. Maybe less code to write. Oh, I remember we have IDEs generating all this boilerplate for us, right? There was something. That's the reason why we still have getters and setters. So we have this point independent computable. As I said, it doesn't matter where I do that. And the good thing is this doesn't need to be the end. So we can break those elements down even further. It doesn't need to be 100,000 elements. It could be 10 million, 100 million elements. And you just break them down in smaller and smaller chunks and distribute them and calculate them independently and in parallel. So if you have a 1,000-node cluster, you can break them down into 1,000 blocks, and you just send them away and say, okay, whenever you guys are ready, just give me back the result, and I'll do the final sum calculation. But I can do this sum calculation on another node again. It doesn't matter. And the good thing is, this sounds very typical and very familiar and very legal for mathematical operations, but it's not a mathematical thing. For example, the perfect way to describe that, look at Google. The website crawl. Website crawling is website indexing. doesn't have anything to do with mathematics at all. But what they do is, hey, they figure out there's a website, so it has links. The download task will be enqueued at some queue, and eventually it will be downloaded. The downloaded source code of the HTML is put in another task. It will eventually be lexed and analyzed. All these analyzing things going to a different task, doing some calculation based on that for the rating, whatever. So it just depends on how small you make those tasks to split them down. This is a design decision, but you can pretty much break down everything into smaller chunks and just parallelize the whole API and parallelize the whole process. And another important thing about those, or if you want to make it right, make sure that it doesn't matter how often you calculate the same thing. That is where you set side effect free. So parsing HTML and doing a lexical search on that, it just doesn't matter how often I do this if I don't write data into a database while doing it. I can do it once, I can do it twice, I can do it 30 times if it fits. I just don't care. I retry it as long as I can, and eventually I get a result, and I put this result in another task, and this task does something. In the end, you obviously have somewhere a non-side effect free task, but then you just need to make sure that, well, in the worst case, the database can handle, or the data model can handle overriding the same data. Okay. Again, demo time. Who's that?
People.
Ask the client for its local memory, because there's none. Something like that. Okay. So we have those three nodes running in the background. I'm starting the client. It will connect to the existing cluster. It will print out the final result we have down here. And if we look at the other nodes, we actually see that there was one operation, there were 5 operations, there were 4 operations. If I run this again, it will have a different distribution. Why is it not equally distributed? Because there is no load balancer. The load balancer is random. It will just pick a random node and will send the operation to it. Why there is no load balancer? Because you can't write a generic one. Every time you want to try, or you try to implement a generic load balancer, you figure out that everything you try just looks like random. The problem is, for a load balancer, you have to have knowledge about the operation, about the runtime, about the memory consumption, about the CPU consumption, about whatever. There are so many factors that it just doesn't make sense to have a general load balancer. A thing that I often tell customers, because they ask, why are you doing this random stuff? Just doesn't make sense. Just build a load balancer. Yeah. And how? You're writing operations, so how do I know what you do? At Ubisoft, I did it for loading the players. It took me like 2 weeks to get a nice load balancing algorithm. So definitely it's not something you just write out of the box. But there's an interface, member selector. You can build your own load balancing algorithm if you want to. Okay. By the way, I said this one looks ugly, and it does. This is not something you just write out of the box right here. Not in a minute, at least. I'm pretty sure you can do this even nicer, or way nicer, with the Stream API. I haven't tried it, but this double loop thing is just ugly. As I said, random looks kind of understandable. This is a pretty easy thing. Okay. Questions to that? Yeah.
In that case, you can still have a listener on your client that says you that everything is computed.
In this case, you get the return futures, and you just wait on the futures, what I did. So this is a standard executor service. I'm not 100% sure. There is CI executor service, but I think that one only adds overloads for submit and execute to directly select a member, to pass in the member selected implementation and something like that. I think there is no listener interface, because you always get these futures, and you can just pass them in. What is there? Let me see. Since we unfortunately still work with Java 6 because we have bank customers, I hope that the way of Oracle with coherence moving to Java 8 eventually will force them to move onwards, and we can do the same thing. But for now, we're not as big as Oracle, unfortunately, and we have to stay with those people. So we can't use Java 8 features, which leads to weird workarounds. We have an incompletable future, but that one has the typical listener possibilities you have with the completable feature from Java 8.
Right. And on that way, you have to wait for every task submitted.
Yeah. And in this case, you would add the callback and have a semaphore or something just counting down, something like that.
Yeah.
I don't think we have the option that the completable feature is where you can add multiple completable features and say wait for all. I think there is something like that in the completable feature from Java 8.
What happens if calculating multiple times? So,
If
so it is being calculated on the numbers.
yeah, the future will throw an execution exception and you just retry. As I said, it's just a standard Java executor service, so you do the same things as with any kind of executor service. The executor service is not the only way you can do distributed computing in Hazelcast. The IMAP, for example, has aggregations where you can just pass in a typical aggregation function, which is normally minimum, maximum, average, all those typical analytical mathematical functions. There is a MapReduce framework which you can use. There is an executor service. Executor service is like a store procedure you send to the data instead of getting the data to your node and calculating. For example, you send an operation to all nodes which increases the salary of all employees by 10%, something you as an employee would have to run every week. The good thing is you don't have to log around the data because as long as the entry processor runs on the partition, there is nothing else going on. So you have an implicit log around your entry processor. Not meant for long-running operations because you obviously block the partition at that point. But if you have to change multiple values on the same partition, it gives you this nice implicit lock around it. Anything else? Nope. Okay. Now we're coming back to the jokes. Who's that? I think she managed to piss off whole Europe in just 2 weeks. It's amazing. No politician made this happen before, but she can. It was absolutely easy. Yeah, and most probably the best picture ever taken. Okay, so again, I think that was pretty easy. It still looks like Java code. The only thing is where you run distributed. Okay, why do we cache data? Because we want to collect and store data in RAM whenever we have time to access them fast. And this kernel is kind of a good thing, because in autumn, it tries to collect as much nuts as possible, it hides them somewhere, and hopefully it will find them under the snow. Otherwise, we can call it a cache miss. Okay, so let's have some fun with caches. There is a short evolution of caches over the last decade, I would say. People started with writing their own caches. They figure out our system is too slow, the database doesn't react or doesn't respond fast enough to my queries, something like that. Maybe you had hibernate in the way that made queries even slower. So we had to create something which cached or which holds the result for a second access. So people started to write their own things. Let's say we wrote our own system. It's called a hamdogger. It's probably the best idea ever. That's a real thing, you can buy this. A hamdogger. Okay, caches are simple. Anybody disagree with that statement? 2? Okay, 3 people. I think 4, 5, 6, 7. Actually, it's the first time that I think more than one person raised their hand. Okay, so caches are simple. I mean, we have a concurrent hash map, we have a put and a get operation, and obviously we call this new class, this record class cache, because we want to make it obvious to our colleagues that it is cache. It's not a concurrent hash map, it's cache. If you want to make this hardcore obvious for everybody, you can call this cache or caching, and you can call this retrieve. Something like that. Then you have a cache. It's a concurrent hash map. We don't have to think about multi-threading. Everything is fine. There's just one small problem.
And really?
Well, yeah. You just put in data, but normally you want to clean up a cache at some point. So what you do is you add a TTL. TTL means time to live. So you say, okay, for example, I have a news site, and there is a very obvious and very common time frame where my news articles are read heavily, which is 24 hours for a normal daily news page. So you say, okay, whenever I create an article, I want it to be in the cache for 24 hours. This is my time to live, and after those 24 hours, just throw it away. If somebody ever wants to read it again, well, just load it for another 24 hours and throw it away again. Okay, you can't read that anymore for a reason, but it still works. It still fits on one slide. It's still easy. So what we do here is our get operation. Whenever you read something, it looks if the key expires. Is the key expired? And if the key is expired, it will remove it and return null. Still, we have a short problem. We still have a memory leak because we probably never ever gonna read the same key again. So there's 12 hours. Bush, Obama, whoever is going. No, Obama can't be the next president again. Bush or Donald Trump, hopefully not, is going to be the next president. And for 12 hours, people reading this article like hell. And after 12 hours, nobody is interested anymore. It's like being president, you have a lot of... Okay, why do we cache data? Because we want to collect and store data in RAM whenever we have time to access them fast. And this kernel is kind of a good thing, because in autumn, it tries to collect as much nuts as possible, it hides them somewhere, and hopefully it will find them under the snow. Otherwise, we can call it a cache miss. Okay, so let's have some fun with caches. There is a short evolution of caches over the last decade, I would say. People started with writing their own caches. They figure out our system is too slow, the database doesn't react or doesn't respond fast enough to my query, something like that. Or maybe you had hibernate in the way that made the queries even slower. So we had to create something which cached or which holds the result for a second access. So people started to write their own things. Let's say we wrote our own system. It's called a hamdobber. It's probably the best idea ever. That's a real thing, you can buy this. A hamdobber. Okay, caches are simple. Anybody disagree with that statement? 2? Okay, 3 people. I think 4, 5, 6, 7. Actually, it's the first time that I think more than one person raised their hand. Okay, so caches are simple. I mean, we have a concurrent hash map, we have a put and a get operation, and obviously we call this new class, this record class cache, because we want to make it obvious to our colleagues that it is cache. It's not a concurrent hash map, it's cache. If you want to make this hardcore obvious for everybody, you can call this cache or caching, and you can call this retrieve. Something like that. Then you have a cache. It's a concurrent hash map. We don't have to think about multi-threading. Everything is fine. There's just one small problem.
And really?
Well, yeah. You just put in data, but normally you want to clean up a cache at some point. So what you do is you add a TTL. TTL means time to live. So you say, okay, for example, I have a news site, and there is a very obvious and very common time frame where my news articles are read heavily, which is 24 hours for a normal daily news page. So you say, okay, whenever I create an article, I want it to be in the cache for 24 hours. This is my time to live, and after those 24 hours, just throw it away. If somebody ever wants to read it again, well, just load it for another 24 hours and throw it away again. Okay, you can't read that anymore for a reason, but it still works. It still fits on one slide. It's still easy. So what we do here is our get operation. Whenever you read something, it looks if the key expires. Is the key expired? And if the key is expired, it will remove it and return null. Still, we have a short problem. We still have a memory leak because we probably never ever gonna read the same key again. So there's 12 hours. Bush, Obama, whoever is going. No, Obama can't be the next president again. Bush or Donald Trump, hopefully not, is going to be the next president. And for 12 hours, people reading this article like hell. And after 12 hours, nobody is interested anymore. It's like being president, you have a lot of security, and after you're being president, there is nobody left. You can just be shot on the street. So that means we never will hit this key after 24 hours. Still not a good solution because it still means we keep those data in the RAM. So as a good Java developer, we all know what the solution to that is. We add some auto cleanup, and it still fits on one slide. And auto cleanup, I guess, is clear, right? We have some background thread running, looking for the values. Is there something expired? Just remove it. That pretty much looks like that. It's very easy. The problem is we have something which is not nice at least. It's not wrong in this case. It's nice together with something very typical, a typical mistake in Java. This is pretty bad. Any idea? It's not the iterator rule, I can tell you that. This is the most common answer. It's a concurrent modification. No, it's not.
Like time zones?
Sorry?
Time zones.
Time zones. Oh, yeah, that could be a problem. Time zones. Yeah. In the worst case, you keep it for an hour longer. Don't think this is too bad.
You are walking the cache.
Right. Wow, it's the first time. What does it mean?
It's the same guy who used the boot.
Right. We have to walk the whole cache, which means it's a linear runtime. It's a big O N. Together, as I said, together with a very common mistake, this is a pretty bad thing. So when you do those things, you don't have this task running over and over again. You see there's just this while loop until you have the iterator, so that means we have to reschedule. Rescheduling Java is the scheduled executor service, a very nice incarnation of the executor service that every Java developer loves. But there are two scheduling methods. There's the fixed delay and a fixed rate. What is the difference?
One starts after a period, after the other ended, and one of the other.
You guys are amazing. Absolutely. So with fixed delay, waits until the last task ends, adds the delay, and restarts the operation, or schedules the new one. At fixed rate, it just doesn't care if something is ready or not. It just reschedules at the rate you pushed it. So imagine you have 5 million elements, you have 20 million elements, and this thing runs for 60 minutes, and you schedule at a time frame of 10 seconds. Because it looked good in your unit test, it worked. The typical things, happy world unit tests. Well, yeah, that can be pretty bad. Actually, unfortunately, and I have to admit that I'm feeling guilty, that it's not a made-up example. We found that in Hazelcast code at some point. And I really hope that nobody ever used the TTL in Hazelcast up to the point we fixed it. It is a bit back in time by now, But still, as I said, this is not a made-in example. This is a very, very common mistake. And it's just 6 lines of Java code. Together with the schedule, it's 7 lines of Java code. How many mistakes can you make in 7 lines of Java, right? It's simple code. There is nothing important. This was only visible because we created a new tool we call simulator. In the beginning, we called it stabilizer. Before that, the intern name was gridfucker. Marketing wasn't happy about that name. I don't know why. We actually tried to convince marketing to call it fritgacker. They weren't happy with that either. Yeah, so by now it's called simulator, and we ran this system, and at some point our service just crashed, and nothing happened anymore. What's going on? Unit tests are happy. Something is very wrong here. And well, I set 32 gigabytes of RAM, so who had to test it on his local machine with a profiler? So I looked into it, and shortly before my Windows machine died, I had like 60 threads doing nothing but expiration. On an 8-core machine, that was even worse. So my Windows machine wasn't really working, wasn't reacting at all. Let's call it that way. I had to restart it. The point I'm making, this is very unobvious code, very unobvious mistake. But if you write your own things, that could possibly be in your code. There are companies doing that. There are open source projects doing that for years. They went through all those hell things, and it's probably better to use one of those instead of writing it on your own. So it was a trap, right from the start. Caches are not simple. There is the JCache specification, and it has about 150 pages for a reason. If you get the requirement document with more than 150 pages for cache, feel free to do your own cache. Otherwise, you probably want to use one of those that are already existing and implementing the cache spec. Okay, custom caches. Then there are proprietary caches. Proprietary caches, I think Coherence was one of the first ones. I think so. Then there was Terracotta, the DSO, the distributed shared objects from Terracotta. Yeah, right? So those things, DSOs doesn't exist anymore. These days everything is cache Terracotta. But there are proprietary caches, and they're good. It's not a bad thing. There are open source caches. This is for some obvious reason a bit bigger. This includes Hazelcast, this includes InfiniSpan, Apache Ignite, EHCache, a couple of other, and interestingly, most of them have a commercial edition, which is Hazelcast, InfiniSpan, Apache Ignite, EHCache, and probably all of the other things. And this is the joke I'm not going to make today. So why do we have JCache? I think everybody knows that's a problem. We all had a lot of different mobiles in the past, and probably everybody has 3 or 4 different chargers with different connectors. The most important and most expensive ones are not even on the site. Apple managed to have a different connector at every single generation of its own mobile phones. They are very consistent. So Oracle Coherence has one plug, InfiniSpan has one plug, Terracotta and EHCache share the same plug, Hazelcast shares a lot with the collections API, not everything. You have this thing which is your custom thingy, which looks completely different from everything else. And eventually somebody came across and said, well, all of them doing the same thing. The use cases for caches are quite small, quite restricted, so maybe we should create something like a general Java spec. We all know how Java works, we have specs. Nobody wants to have a spec like JPA, which is in 2.2, 2.1, and still doesn't have many-to-many relations.
It does.
It does?
Yeah,
no, it
more or
doesn't.
less.
Yeah, proprietary implementations. Okay, yeah, it has in a different way. So JCache is...
Why not swap there? It was the most obvious when you in the previous slide. Because
Yeah,
like
good question.
Ago,
there are no more plugs open. So these are normally the distributed implementations. That's probably the reason. EH-cache is not completely true because EH-cache normally runs as a local cache. It has some basic replication mechanism, but since Terracotta shares the same API with EH-cache, it kind of fit on the street. Yeah, but you're right. Guava definitely, or is it Guava? Yeah, it was Google Collections. Now it's Google Guava, or is it the other way around? Something like that. They changed it at some point and mixed it up. Yeah, probably even one of the most used versions. Definitely, yeah, good hit. Just put it under Google Collections, under Java Collections because they implement mostly implement the original ones that have some additional things. And JCache is like the mini USB or micro USB, the thing we all love today, and we're gonna miss in the future since there is now USB-C. And Apple and Huawei start to use that. Well, as long as we can turn it 180 degrees, it needs to be better. So I would say it feels like success because, as I said, everybody's doing the exact same thing. You have, just on one slide, you had 6 different APIs, and now you have 1. You can use that, and it doesn't support all use cases by now. So JCache 1 was released end of last year, October, September, something like that. Maybe
it was announced on Java 1 last year, yeah.
Yeah, so October. And it supports all the synchronous use cases. It's still missing asynchronous, and we all love to do reactive programming these days because everybody claims that reactive programming is super cool. Hopefully, JCache 2 will have asynchronous functions. It will hopefully have transaction support. I hate to do that. But there's one good use case for transactional support in a cache. And there's a third topic that was pretty important that I just forgot. It wasn't important to me at least. So if everything goes right, JCache 2 will be the last API changing version in the near and far distance. And I hope this is going to happen. As I said, we don't want to have another JPA, which is still messing around with proprietary additions. There are probably further versions of JCache, but hopefully just contain integrations and stuff like that. So whenever you're going to start to use a cache today, go for JCache, definitely as a reason. Use any of those implementations. All of the guys that were on the slide have a JCache implementation. I think Guava has one too, as far as I know. And the good thing is you can just exchange them. You can use for your local caches tests, you can use EH-cache, you can use Guava, and if you're going production, you just plug in anything else, anything distributed, like Org, Coherence, Apache Ignite, InfiniSpan, Hazelcast, whatever. That is the main goal, just not to have changing source code. Okay, and that is really the last part of the deck. Whoever finds the shameless plug can keep it. 3 slides. We heard all of that. It's just Java Collections API. We've seen that. Maps, lists, add queue. Whatever is out there. Concurrency API. We've seen the Explorer service. There's semaphores. There's locks. There is atomic longs. Pretty much everything you want to have and probably don't want to use, like transactions and locks. Transparent data distribution, we've seen that as well. Transparent in this case means as long as you can tell us how to serialize something, we can do that. It's a drop-in replacement for most of the cases. Rod Johnson, who knows Rod Johnson? I think next time you try that, your arm will just fall down again. No power left. Rod Johnson, the creator of Spring. The guy that wrote the book, EGB done right, EGB whatever. Nobody remembers the book, but everybody knows Spring these days. They seem to have something made good. The interesting thing about Spring is that Spring was his demo implementation of the ideas he wrote in his book. That's a good story. And he's one of our board members. And when he first found out found out about Hazelcast, he said it's disruptively simple. In the beginning I said Hazelcast is all about simplicity, and that is the statement you want to have, because that is the main goal. So, time to be happy, Apache license, I said we have a commercial version on top of that, but since I'm doing all this open source and community stuff, I am the guy who says go for hazelcast.org, don't go for the .com site, download the open source version, there are all the data structures, all the computation functionality, just get started, love it, and if you have some money left, we're happy to pay the next payroll check, but you don't have to. And with that picture, by the way, didn't work in Brazil for a reason. They were not laughing. You can do it. Any more questions?